Understanding piezoelectric constants. What do your phone's camera, a medical ultrasound, and an industrial welder have in common? They all speak a secret language. Let's decode the key terms that make this technology possible. Piezoelectric materials are the invisible engines in countless devices, converting electricity to motion and back again. But how do you choose the right one? The answer is on the datasheet if you can read it. Datasheets often look like a cryptic cipher, but three critical parameters, d33, k, and qmem hold the key to performance. Understanding them is crucial for any successful design. Let's start with the material itself. The magic starts in the crystal lattice. Below a critical temperature, the central atom shifts, creating an electric dipole. This tiny imbalance is the fundamental source of all piezoelectric effects. But how do we harness it? First, the material's chemistry is tuned to a special peak performance recipe. Then, a massive electric field aligns all the microscopic dipoles, activating the material. Next, we'll see what properties this process creates. The first constant is d33, the charge coefficient. It tells you how much the material moves when you apply voltage or how much charge it generates when you apply force. It's a measure of action. This action comes from two sources: the lattice stretching and domain walls moving. Materials with mobile walls have a very high D33, making them great for sensitive sensors or actuators needing large motion. Next is K, the coupling factor. It's not efficiency, but a measure of how effectively electrical and mechanical energy can be converted. Think of it as the stiffness of the connection between the two domains. A high K factor creates a wide gap between the material's resonance frequencies. This allows the device to operate over a broad range of frequencies, which is essential for applications like advanced sonar or medical imaging. Finally, we have QM, the mechanical quality factor. This constant is the single most important parameter for high-power devices. It determines whether a transducer will perform powerfully or simply burn out. Think of a crystal glass versus a plastic cup. The crystal high QM rings, storing energy, the cup low QM thuds, turning energy into heat through friction. This heat is the enemy of power, ultrasonics. Soft PZT is created by adding donor dopants. This makes the internal domain walls highly mobile. The result is high sensitivity and displacement, but also high internal friction, which means low QM and more heat. Hard PZT is the opposite. Acceptor dopants are added to chemically pin the domain walls, preventing movement. This lowers sensitivity but dramatically increases QM, allowing for high power use with minimal heat. This creates a fundamental trade-off. You can have high sensitivity or high power handling, but not both in the same standard material. The engineering choice is always about finding the right balance for the job. Here's how different material grades stack up. Notice the clear inverse relationship. As D33 goes up, QM goes down. This table guides engineers to the right starting point for their application. For high-power ultrasonic welding, PZT-BA is the choice. Its extremely high QM means it can handle immense power with very little self-heating, ensuring a stable and reliable process. Here, power trumps sensitivity. In medical imaging, the goal is the opposite. Faint echoes return from body tissue. A soft PZT like PZT-WH with its massive D33 acts like a supersensitive microphone, ensuring a clear diagnostic image. Ultrasonic cleaning needs a balance. PZTC is the Goldilocks material enough Q-meter to run without overheating, but a stronger D33 than PZT-BA to create powerful cleaning cavitation. It's the best of both worlds. What happens when you choose wrong? Using a low QIM material in a high-power device creates a death spiral called thermal runaway. Internal friction generates heat, which increases losses, creating even more heat until failure. In the end, it's a symphony. Think of D33 as your volume knob, as your transmission for bandwidth, and QM as the guardian protecting your device from burnout. Mastering them is key to success.